Welcome, Nocturnal Minds, aboard. Your learning journey starts now. So, we've seen how thought experiments can be powerful tools, but sometimes they lead us down paths where the very foundation seems shaky, especially when it comes to what we value. This brings us right into the heart of our discussion today: values in science. Think about it. Science is this towering pillar of modern life, supposedly built on pure objectivity, rationality. We trust it implicitly, yet flip through history, and you find science used as a justification for some of humanity's darkest chapters. Think eugenics or Stalin's purges. It's a stark contradiction. This tension really hit the logical positivists hard. They felt their mission wasn't just academic, it was about survival. They argued fiercely for drawing a line between genuine science and pseudoscience. Why? Because they saw pseudoscience as a dangerous mask, using the language of facts to smuggle in values, emotions, essentially anything but reason. Their big idea was simple: real science has to connect directly to observable experience. Anything else? Just noise, emotive expressions without any grounding in reality. This fear, this drive to protect science's purity, really shaped Anglo-American philosophy, leading to this powerful, almost dogmatic belief that true science must be value-free. Now, fast forward a bit. Philosophers today aren't quite buying that old emotive account of values anymore. It feels too simplistic, but that initial worry, the fear that politics or other societal values could poison the well of scientific inquiry, hasn't completely vanished. Many still feel uneasy if political agendas start dictating research priorities, manipulating results, or deciding how findings should be used. It feels wrong, doesn't it? However, the picture is more complex. Look at the actual practice of science, and you see social values everywhere, shaping what gets funded, who does what questions are asked, and how discoveries are applied. So, where does that leave us? Well, some contemporary philosophers have taken a fascinating turn. They argue that maybe, just maybe, social values aren't always a bad thing for science. Perhaps they can even be beneficial. That's the landscape we're navigating now. Our goal here is to untangle this knot, to figure out exactly how values play into scientific knowledge, and crucially, to show how we can maintain a sense of rationality, even in a world where values clearly matter. Okay, let's get specific. When we talk about values influencing science, we need to make a crucial distinction. Think about social values first. These are the things a society generally agrees are good things, like justice, having decent health care for everyone, fighting diseases, keeping the nation safe, you name it. Now, it's pretty obvious these things shape science. Where does the money come from? Who decides what problems are worth solving? What kind of knowledge are scientists trying to produce, and why? And what happens to the results once they're out there? All these are heavily influenced by these broader social values. You could look at any of these influences and say, maybe we should have prioritized different values here. Better values lead to better scientific practice. Makes sense. But, and this is a big but, noticing all these influences doesn't automatically mean that the scientific knowledge itself becomes relative to those values. It's like saying the chef's desire for a delicious meal influences the cooking process, but that doesn't mean the taste of the cake is defined by the chef's desire. The core question remains: is the knowledge produced, the truth captured itself, dependent on these social values? So, the argument presented here leans towards saying yes, scientific knowledge itself seems to be value-free, at least in a fundamental way. How do they argue this? By focusing on what makes scientific knowledge successful. Forget the social pressures, the funding battles, the political agendas for a moment. Does the knowledge hold up? Is it empirically adequate? Does the theory fit the data, explain the observations, make the right predictions? If a theory does all that, it counts as scientific knowledge, regardless of whether it aligns with our current political climate or popular social trends. Empirical adequacy, this ability to correctly accommodate relevant evidence, seems to be the bedrock. And this, the argument claims, isn't something like justice or equality, which are clearly social values. It doesn't seem to be something that's just handed down by society. It looks like something that stands apart, a standard that science sets for itself based on its engagement with the world. So on the surface, it seems like scientific knowledge is indeed value-free. But wait, hold on a second. Isn't this ignoring the historical shifts, the paradigm changes Kuhn talked about? Doesn't science constantly redefine what counts as good evidence, what theories are acceptable? This essay argues precisely that. It says, okay, scientific knowledge is value-laden, but not in the way you might think. The necessary values, the ones that ultimately determine what counts as knowledge, are epistemic values. What are these? Think about the qualities we look for in a good scientific theory. Is it simple? Does it unify different phenomena? Is it accurate? Does it make novel predictions? Does it have broad explanatory power? Is it empirically adequate? These are epistemic virtues. They are the standards we use to judge theories. Now, here's the twist. Social values can only play a legitimate role in shaping scientific knowledge if they somehow justify adopting certain epistemic values or set standards for how we realize those values. For example, a social value like public health might justify prioritizing predictive accuracy in medical research. But if social values start dictating conclusions directly, bypassing these epistemic standards and ignoring empirical success, then that's corruption. It's like saying, we believe X is true because it serves our interests, regardless of whether it fits the data or meets our criteria for a good theory. This view tries to find a middle path, acknowledging value influence but setting clear boundaries. So, this gives us a two-tier model. Imagine a pyramid. At the base, you have the social values, the desires, and needs of society. These can provide reasons for choosing certain epistemic values and standards at the next level up. Think of the Bergen School meteorologists again. Their need for forecasts justified redefining weather phenomena. Then at the top, you have the epistemic values and standards themselves, like simplicity, unification, or predictive accuracy. These in turn provide the justification for accepting specific scientific theories. A theory is good because it satisfies these values. This model avoids the extremes. It doesn't say social values are always toxic, nor does it claim only perfect preordained social values can ever help. Instead, it shows a pathway where social values can feed into the scientific process in a rational way, provided they respect the epistemic structure. And this becomes really interesting when we combine it with Kuhn's insight that these epistemic values and standards themselves aren't fixed. They change over time, driving scientific revolutions. This challenges our usual ideas about scientific progress and objectivity, suggesting we need new ways to understand them. Exactly, and Kuhn gives us clues about how these normative shifts happen. The essay identifies 4 key types of value commitments that can shift during the development of scientific knowledge. First, value-laden phenomena. What counts as the core subject matter? Think about chemistry. Before Lavoisier, alchemists were obsessed with qualities like metallic luster. Lavoisier shifted the focus to quantitative changes, like weight gain during combustion. Different groups valued different kinds of phenomena as essential. Second, value-laden inferences. How do we get from observations to theories? Newtonians insisted on strict induction, generalizing from observed cases. Either theorists, grappling with unobservables like heat or light carriers, embraced abduction, reasoning from effects to causes, even if the cause wasn't directly seen. Third, value-laden theoretical virtues. What makes a theory good? For a while, action at a distance in gravity was frowned upon. Mechanistic explanations were preferred. Later, the ability to make novel predictions became highly valued. Einstein even rejected quantum mechanics partly because he felt it violated locality, a deep-seated principle for him. Fourth, value-laden standards of empirical accuracy. How close does a prediction need to be to the measured value to count as support? Without agreement on acceptable error margins, how can anyone say data supports a theory? These aren't just minor details. They represent fundamental shifts in how a scientific community defines its goals and methods. So, how do we wrap our heads around this? The essay suggests an analogy. We already know that human knowledge isn't absolute. It's always relative to the evidence available. Well, this value-ladeness thesis extends that idea. It says knowledge is also relative to the appropriate epistemic values and standards that a scientific community adopts. Think about it. The ideal of objective evidence isn't some timeless universal constant. It changes. Of course, there are strong continuities within any given field, like how astronomers have always cared deeply about planetary motion. But across the history of science, traditions undergo major transformations in how they define the relevant phenomena. What kind of inference is needed, what virtues theories must possess, and what counts as accurate enough. It's a dynamic, evolving set of norms. Okay, fine, but why believe this value-ladeness thesis? What justifies it? Let's compare this argument to Helen Longino's influential work from 1990. Longino starts with the classic problem of underdetermination, the idea that observation data never uniquely determines a single best theory. There's always ambiguity. She argues that, because of this gap, scientists must bring in their background assumptions, including wider social values, to bridge the gap and choose between theories. On her view, values fill the logical void left by pure inference. But the argument here pushes back. It says, starting with underdetermination isn't the strongest way to argue for value-ladenness. Why? Because lots of philosophers accept that confirmation isn't purely logical, without jumping to the conclusion that values are the answer. Realists talk about inference to the best explanation. Naturalists talk about reliable belief-forming mechanisms, and neither necessarily involves value-ladenness in the same way. So, where does this argument get its strength from history? It starts with Kuhn's analysis of scientific revolutions. The key insight isn't just linguistic or ontological change, but a shift in the normative landscape. The problems, data, standards, and values a community thinks are essential for genuine knowledge. This historical shift, the argument claims, is what truly reveals the value-laden nature of scientific knowledge and forces us to rethink concepts like rationality and progress. Alright, so, if knowledge is value-laden, how do we actually spot these values in action? How do we tell when a shared belief is just a regular empirical assumption versus a deeper epistemic value? The essay proposes looking at three things within a scientific group's behavior. First, their choices. What theories do they accept? What do they reject? Second, their reasons. Why did they make those choices? What justifications do they offer? Third, the principles they invoke in debates. What underlying standards or principles do they appeal to? If attributing a particular shared epistemic standard, say, a preference for unified theories, helps explain all three of these aspects, why they accept certain theories, why they reject others, and what principles they use in arguments, then that strengthens the case for value-ladenness. It's about finding the underlying normative commitments that shape the entire practice. Let's apply this to the classic case, alchemy turning into chemistry. The standard story is simple. People change their beliefs, and the new beliefs match the data better. But the value-ladenness view offers a richer picture. Look at the choices. Alchemists focused on explaining things like the color and feel of substances. Early chemists focused on things like weight changes during reactions. Look at the reasons. They weren't just seeing different things. They were committed to different kinds of phenomena, being the essential stuff of chemistry. And look at the principles. There was an implicit shift in what counted as a core chemical phenomenon. This explains why, even though the new chemistry couldn't immediately explain why all metals have metallic qualities, alchemists dropped that question entirely. It wasn't just about better data fitting, it was about a fundamental shift in what they valued as the domain of chemistry. This shift in epistemic values explains both the gains and the losses in the scope of scientific explanation. So, we've established that a shared consensus on epistemic values is necessary for scientific knowledge. You can't have science without agreeing on what counts as a good theory. But is it enough? No, the argument says. Just having shared values doesn't guarantee knowledge. Knowledge is contingent on three other things. First, the world itself has to be structured in a way that allows for knowledge the realist perspective. Second, the scientific communities need to be able to negotiate and revise their shared values when they clash or prove inadequate, the social constructivist ang. Third, and perhaps most importantly, they need to actually develop theories and techniques that achieve empirical success according to those standards, the empiricist emphasis. It's a package deal: shared values, a suitable world, effective negotiation, and empirical success. All are needed. Now, let's tackle some objections. First up, the postmodern critique. Isn't this whole epistemic versus social values distinction just splitting hairs? Aren't epistemic values just another type of social value, governing how we evaluate theories? The response is nuanced. Yes, epistemic values are social standards in the sense that they emerge from and are maintained by scientific communities. But the crucial difference lies in how they function. Scientists often have good reasons for embracing certain epistemic values, and these reasons can be rooted in social values. Think of the meteorology example again. The social need for forecasts justified the epistemic shift towards atmospheric physics. However, the link between social values and knowledge is only rational if the social values effectively translate into appropriate epistemic values and if the resulting knowledge claims are backed by empirical success. It's not just about having values, it's about having the right kind of values justified appropriately and leading to successful knowledge. Let's flesh that out with a meteorology example. Imagine Wilhelm Jerknes and his team in the early 20th century. They weren't just doing abstract physics, they were driven by a powerful social need. Pilots needed reliable forecasts, fishermen needed them, farmers needed them. Reliable weather prediction was a high priority. This practical social interest motivated them to redefine what weather even meant, expanding it beyond old folk wisdom to include the actual atmospheric motions and conditions. This new definition of weather phenomena became a key epistemic standard. It justified their entire quest to build a physics of the atmosphere. So, you see a reasonable social value, the need for forecasting, providing a solid reason for adopting a new epistemic value, redefining the domain of study. The social value didn't dictate the conclusion. It provided a rational basis for changing the epistemic framework. But can epistemic values ever be justified independently of social values? Absolutely. Consider astronomy. Historically, understanding the stars and planets was driven by various social aspirations: navigation, calendar making, agriculture, even figuring out divine will. But look what happened. Astronomers eventually gave up on astrological interpretations. They stopped trying to read fate in the heavens. Yet, the epistemic value of understanding the precise movements and positions of celestial bodies remained incredibly central to the scientific enterprise. People kept studying it, developing sophisticated models long after the original social motivations faded. This shows that while social values often kickstart or shape scientific practice, the core epistemic values that define what counts as astronomical knowledge aren't reducible to those initial social drivers. The pursuit of understanding the cosmos retained its scientific legitimacy even when the why shifted. Objection number 2. Universal values. Can't we just point to a set of universal epistemic virtues that all science aims for? Things like empirical success, predictive power, unification, simplicity, solving problems effectively. This sounds plausible. These do seem to distinguish science from, say, pseudoscience. But the counter-argument is that these universal values are too abstract to function as criteria on their own. They need to be fleshed out with local standards. Predictive accuracy is great, but how accurate is accurate enough? Unification is good, but which phenomena should be unified? Does unification require causal mechanisms, or just mathematical elegance? Saving the phenomena is important, but which phenomena matter most? What counts as a useful theory for saving them? What kind of reasoning counts? And crucially, does successfully saving phenomena give us reason to believe the theory is true? Different scientific communities throughout history have answered these questions differently. Their specific commitments to certain epistemic values and standards are what makes scientific knowledge possible for them. Next, objections from normative naturalism and externalist reliabilism. Normative naturalists try to sidestep value relativity. They say, okay, practices are value-laden, but we can empirically evaluate which practices are most effective at achieving the ultimate aim of science, like discovering truth, the problem. Defining truth itself involves value-laden choices, and judging effectiveness requires comparing practices, which also involves values. You can't escape the value-ladenness by appealing to a neutral aim like truth. Externalist reliabilists take a different tack. Knowledge is just belief formed by a reliable process. The issue here is defining reliability. How do we know if a process is truth conducive without already having some standards for what counts as truth or reliable reasoning? Often, these standards involve value-laden disputes, like whether inference to the best explanation is reliable. So, the argument goes, reliabilism doesn't offer a value-free escape hatch either. It just pushes the value-ladenness into the definition of reliability itself. The big fear, of course, is relativism. If knowledge is value-laden, doesn't that mean everything is just opinion, undermining rationality, objectivity, and the very idea of scientific progress? The response is a resounding no, if we understand the role of values correctly. Rationality here isn't just about internal consistency. It includes practical rationality in choosing epistemic values. Groups choose values based on good reasons, which might come from social concerns or from epistemic considerations themselves. Think about the shift from strict induction to the method of hypothesis for either theories, driven by the need to explain new phenomena, a rational response to inconsistency. Objectivity isn't about being detached from all values, but about being objective relative to the agreed-upon epistemic standards of the community. Progress is possible because these shifts in values are often driven by good reasons, resolving puzzles, achieving better empirical success, and lead to a deeper or broader understanding of nature. It's a dynamic rational process, not a descent into arbitrary preference. So, if we accept that scientific knowledge is value-laden, what can we do with that insight? The essay suggests it opens the door to a critical theory of scientific argument. The idea is to make scientific debates more rational by bringing hidden value commitments into the open. How? By using the value-ladenness thesis as a tool for critical analysis. This could involve identifying the rival epistemic value commitments lurking beneath the surface of a scientific controversy. Are they arguing about simplicity, or about unification, or about predictive power? Investigating the social values that might be driving those epistemic commitments. Are they reasonable, critically examining the social values embedded in a scientific practice itself? Are they justified by making these normative differences visible and subject to scrutiny? We can potentially make scientific discourse more transparent and ultimately more rational. Let's look at a real-world example, the air traffic controllers' strike during Reagan's administration. The controllers were striking over brutal working conditions described as oppressive stress. Their advocates, the union and safety officials, decided to frame this using the language of scientific stress, linking it to heart disease, ulcers, etc., hoping to gain legitimacy. Bad move. Congressional hearings brought in experts who defined stress scientifically as measurable physiological responses. According to these experts, the ATC's work wasn't actually stressful. The scientific facts, interpreted through one dominant epistemology, worked against the controllers. But what if the ATCs had defined stress differently? What if stress referred to the crushing pace, the lack of control, the life or death decisions, the resulting sleeplessness and irritability? This experience-based definition points to different standards, different causes, perhaps different interventions. A different scientific inquiry guided by epistemic values valuing lived experience and organizational factors might have generated counter-knowledge supporting the controller's claims. The tragedy highlights how invisible epistemological politics can be devastating. So, wrapping this up, the value-ladenness thesis isn't just an academic curiosity. It's a potential tool for improving scientific practice and public understanding. It helps actors in conflicts recognize the hidden interplay of social and epistemic values. It makes the epistemological politics of science visible. When we can see these differing commitments, when we understand that our choices about what to value, how to know, and what to believe are deeply interconnected, we serve rationality better. Scientific progress, the advancement of knowledge, and even uncovering new facets of reality become part of a coherent human story of cognitive development, provided, of course, That the commitments guiding our scientific endeavors are well-reasoned and empirically validated. For those interested in digging deeper into these thorny issues, the footnotes provide a fantastic starting point. Works by Lakatos, Kuhn, Lawton, and others are essential reading for anyone wrestling with the role of values, rationality, and progress in science. They represent the core debates and developments in this area over the last few decades. Alright, shifting gears completely now. We've explored a messy world of values in science. Now, let's dive into another fundamental concept that seems equally pervasive yet philosophically fraught: causation. Bertrand Russell, back in 1913, famously declared causation a relic, something physicists had abandoned because it didn't exist. He wasn't alone. Many prominent thinkers of the time shared this skepticism. Yet, if you just glance at any modern scientific journal, you'll find causal language everywhere. Caused by, Hall effect, major cause of death, it's unavoidable. This tension between philosophical doubt and scientific ubiquity makes causation a fascinating puzzle for philosophers of science. So, how do philosophers try to tackle this? The main goal is to analyze causation, to figure out what it really is. Broadly, there are two camps. Reductive analyses try to boil causation down to non-causal terms. Think translating a causes B into something involving probability, counterfactuals, or laws without using the word cause. Non-reductive analyses, on the other hand, try to map out the relationships between causation and other concepts, like probability or mechanisms, showing how they interact, but without claiming to eliminate causation itself. Why the push for reduction? Two main reasons. Epistemologically, causation seems hard to observe directly. We see the billiard ball strike another, and the second moves, but the act of causing itself is hidden. So, we need a way to translate causal claims into something observable. Metaphysically, there's Occam's razor: keep things simple. If we can analyze causation away in favor of more fundamental concepts, why posit it as a separate entity? But any theory of causation faces some serious hurdles. It needs to handle several tricky cases. First, distinguishing real causation from mere coincidence. Just because event A always happens before event B doesn't mean a causes B. Remember the fruit example. Eating it just happened to coincide with deaths later. No causal link. Post hoc ergo propter hoc is often a fallacy. Second, the asymmetry problem. Usually C causes E, but E doesn't cause C. Time order is often a clue, but what if time travel or closed time-like curves exist? We need a deeper account of directionality. Third, distinguishing direct causes from common causes. Smoking causes both stained teeth and lung cancer. But stained teeth don't cause lung cancer. They share a common cause: smoking. The theory needs to handle this. Fourth, the preemption puzzle. Imagine a building with a main power grid and a backup generator. Usually, the grid causes the lights to be on. The backup generator is just sitting there, ready to take over if the grid fails. The theory needs to correctly identify the grid as the cause in normal circumstances, ignoring the backup. Passing these tests is crucial for any viable theory. The oldest and perhaps most famous approach is the regularity theory, tracing back to Hume. He basically said, causation is just constant conjunction. If every time you see A, you also see B, and only B, then the cause is B. John Stuart Mill pointed out this was too strong, so John Mackey refined it with his Ionist conditions: insufficient but non-redundant parts of an unnecessary but sufficient condition. This allows for probabilistic causation, where C is part of a set of factors that together guarantee E, but C alone isn't enough. Hempel tried to strengthen this by requiring the regularity to be grounded in laws of nature. But these regularity theories run into trouble. Capturing the asymmetry of cause and effect is hard without just defining it away. Handling common causes is tricky, as you can find regularities involving A and B separately. And they still struggle with a preemption problem, the backup generator case. Given quantum mechanics hinted at indeterminism, maybe causation isn't about strict necessity, but about probability. Probabilistic theories say a cause raises the probability of its effect. Mathematically, P of E given C is greater than P of E. But wait, isn't that just like the regularity problem? Coincidences could still look like probability raising. So the theory needs to appeal to objective probabilities, not just frequencies. This brings in tricky questions about probability interpretation and directionality. Knowing P of E, given C, is greater than P of E doesn't tell you about P of C, given E. Simple pairwise probabilities won't cut it. The solution involves conditional probabilities and screening off. If C causes both A and B, then knowing C screens off the probabilistic link between A and B. This helps distinguish common causes from direct causes and infer direction. But defining what factors to hold fixed in K requires causal concepts, making this approach non-reductive. And guess what? It still struggles with preemption. Another influential approach comes from law and counterfactuals. The core idea is borrowed from legal reasoning: a cause is B if and only if. The counterfactual, if A hadn't happened, B wouldn't have happened, is true. How do we check this? By looking at possible worlds. The counterfactual is true if in the closest possible worlds where A doesn't occur, B also doesn't occur. The big challenge is defining closeness. Worlds where E doesn't happen should be closer than worlds where E does, even if the latter differ only in A. Violations of natural laws should count as much bigger differences than minor variations in events. This metric needs to capture genuine causal connections. Directionality also needs to be built in, preventing counterfactuals from backtracking. But here's the kicker. Counterfactual theories often fail with preemption. In the power grid case, if the grid failed, the backup would start. So, the counterfactual, if the grid failed, the lights wouldn't be on, is false, even though the grid normally causes the lights to be on. A tough nut to crack. Manipulability theories take a different tack. They say causation is about agency. Causes are means to produce effects. We intervene to bring about C, and we expect E to follow. Crucially, this relationship should hold, even if we manipulate C in novel ways. If E were the cause of C, manipulating C wouldn't reliably produce E. If A and B are both effects of C, manipulating A shouldn't produce B. This focus on intervention naturally captures directionality. But isn't this too human-centric? What about causation in the distant past or in astrophysics, where we can't intervene? The response is to characterize intervention neutrally as an independent causal factor overriding normal processes. Still, this approach is non-reductive because intervention itself is a causal notion. And, surprise, surprise, it runs into the same preemption problems as counterfactual theories. Manipulating the power grid doesn't control the lights because of the backup. Finally, let's look at process theories. These shift focus from discrete events to continuous causal processes. Think baseballs, photons, sound waves. They contrast these with pseudo-processes like shadows or spots of light. A key difference is that real processes are limited by the speed of light, unlike pseudo-processes. How to tell them apart? One leading idea is that causal processes transmit conserved quantities like energy, momentum, charge. A baseball carries energy. A shadow doesn't transmit energy. It just reflects it from the source. This seems promising. It neatly solves the preemption problem. Electrons carrying charge from the grid to the lights constitute a causal process, while the backup generator doesn't have such a process to the lights in this scenario. However, it doesn't offer much new on the directionality problem. If there's a process from C to E, there's one from E to C along the same path. So the usual trick of defining the earlier event as the cause is still needed. So, where does this leave us? After exploring all these different attempts to analyze causation, the verdict is clear. There's no single theory that has won the day. Philosophers haven't settled on one definitive account. However, despite the ongoing debates, significant progress has been made since Russell's skeptical pronouncements. Causation is no longer viewed with the same level of suspicion. Each of these theories, regularity, probabilistic, counterfactual, manipulability process, offers valuable insights into different facets of our intuitive understanding of causation. The quest continues, but we understand the terrain much better than before.